Hi, everybody. Welcome to my presentation at Connected Data London 2021. I'm Alena. I'm a computational linguist at Cororean, and today I'm going to talk about Cororean's approach to data taxonomization. It is no secret that AI has been very successful at tackling different NLP tasks recently, so we embarked on a little quest as well, hoping to find an efficient machine learning powered solution for taxonomy drafting that would make the life of taxonomists just a bit easier. So today I'll walk you through our taxonomization journey and demonstrate what we've achieved on the example of interactive terminology for Europe. Before I start, just a few words about Cororean. Cororean is a unique taxonomy ontology management system that caters for needs of large-scale knowledge repositories. Our multilingual knowledge system brings together the best of two worlds, terminology management systems and knowledge organization systems. We unify knowledge with language by combining concept maps, which are technically knowledge graphs, with concept-oriented language-agnostic terminology modeling. We strive to convert data into knowledge and to provide an intuitive and user-friendly environment for its management. And today I'm going to talk about collaborative taxonomization and demonstrate how AI can lend taxonomists a hand in their daily work. I'll briefly introduce the resource we got for taxonomization and walk you through our study and two approaches that we chose to test. We'll also talk about the benefits of our collaborative approach and briefly have a look at a typical industry scenario, just to show you how these drafted taxonomies can be leveraged in practice. So let's talk about structured data. In our world, structured data is highly organized and can be understood by machine language. It is attractive because it is possible to manipulate it in a very straightforward way. It is possible to link it, extend it, search it, and so on. Another advantage of structured data is that it is very comprehensive and it provides useful information as well as helps algorithms and companies rely on more than just paper-based system. Now, there is this resource, which is called Interactive Terminology for Europe, IATE, and it holds a large part of the textual knowledge of the European Union. It has almost 1 million concepts, storing also multilingual terms and metadata. But it can only be accessed lexically, and while database concepts have crosslinks and metadata, they still kind of stand alone. So we thought, what can be done to bring in some structure? What if IATE were taxonomized? Taxonomization in this presentation is basically linking of related concepts into knowledge graphs, resulting in a full-fledged ontology. This way, the data could not only be consumed by linguists, but would also become accessible by the machine-readable SPARQL endpoint. It would become a powerful resource for AI projects and particularly within a segment of small and medium enterprises that rarely have the means to create multilingual formalized knowledge of their own. So our objective was to investigate if, given recent scientific advances, we could facilitate a speedy creation of a deeply structured taxonomy. Essentially, we want to turn a flat list of concepts without relations between them into hierarchical, machine-accessible knowledge graph. Now, to test our hypothesis, we chose two scenarios, manual and semi-automatic taxonomization. In the first scenario, a linguist took a flat list of concepts and turned them into a structured taxonomy, establishing broad and narrower relations between the concepts. In the second scenario, a machine learning powered algorithm drafted the taxonomy, which was later curated by a linguist. In both cases, the taxonomies feature not only initial input concepts, but also the established relations between them and high-level parent node that bring a meaningful structure into the taxonomy. I want to emphasize here that we did not aim for in-depth review of semantic coherence within the resulted concept clusters. We rather focus on comparison of measurable parameters such as working hours, amount of transactions in the software, and number of relations created. To make our taxonomies a bit more comparable, we established that Both shall share 5 identical top-level nodes, such as entities, instruments, medicine, social aspects, and miscellaneous. And parent node may not have more than 20 to 25 children. Of course, the linguists worked with input concepts that were identical. And I want to also mention that our curators are not domain knowledge experts, yet they were very well familiar with the used software. So, manual taxonomization. When approaching manual taxonomization, curators' strategy was to move from concept to concept, starting from the top-level nodes and establishing broader, narrower relations, later diving into the nodes further down in subtrees. This top-down method requires several passes through the data, going from general to specific. The curator has also exploited the metadata of the terms, just like on this concept card for abnormal mortality. Cororean's concept card is basically a preview widget for the whole concept information. It usually contains the terms of the 2 currently selected languages, domain values, here statistics and demography and population, as well as the definition to give a quick encyclopedic-like hint what a concept is about. Since initially concepts were sorted alphabetically, the taxonomists had to constantly jump from one context into another, and that would most likely be semantically far away. Of course, the taxonomy software provides a set of capabilities and interaction functionalities to comfortably restructure the data. Like here, we see the concept inflammation being dragged from diseases to immune system. Note how the red dotted line shows the relations to be deleted, and the green solid line is the new the relation that is being established. So this highly visual feedback helps the taxonomist to review the effect of the drag and drop before confirming the action. For the curator, it was quite tedious to work through the concepts, despite all these little helpers. It was perceived just as a tiring task, and the progress was difficult to measure and also to follow. It felt like one big mountain to climb without any intermediate milestones, and the question, how far are you, was difficult to answer. While the task is similar to what in taxonomy modeling is known as card sorting, it turned out to be very difficult to achieve with hundreds of concepts. It may work fine with a few dozen concepts, but it gets tedious with so many. So the curator felt frustrated with the task, but we can state that the created taxonomy is the pure result of intellectual human capacity, not influenced by any additional language models or any additional algorithms. For automatic taxonomy induction, we came up with a combination of several algorithms. In the context of this study, each IATE COVID entry comprises concatenated terms and synonyms of a concept. So first, we vectorize the input, which is essentially converting text tokens representing each concept into dense vectors of numbers. We've used publicly available past text word embeddings, but of course, you're free to go with your favorite flavor of word embeddings. Then we calculate a pairwise cosine similarity for all combinations, forming a similarity matrix. And here there are numerous metrics that one can choose from, such as cosine similarity, Euclidean distance, Manhattan distance, and so on. It's your choice. So to create a graph, each node is represented by an input concept. And to form the vertices of the graph, we establish a threshold. Basically a median cosine similarity of all the given similarities. And if 2 concepts have a similarity higher than the determined threshold, an edge is formed between the nodes that correspond to these 2 concepts. The formed edge will then have the similarity score as a weight attribute. So ultimately, all combinations of concept nodes are checked to see whether a connection between them will be formed, hence resulting in an undirected weighted graph. Subsequently, we use the Louvain algorithm to reveal nodes that are more closely related to each other, and the process is executed recursively in order to further break down clusters into subclusters. The produced taxonomy starts with a root node and expands until the leaf nodes reach the input concepts. The automatically generated intermediate branch nodes are labeled with temporary IDs that are to be after named manually. The algorithm is essentially forming concept clusters as concept nodes form clusters with a common parent node. Also, it's worth mentioning that neighboring cluster concepts are semantically closer than clusters farther apart in the taxonomy. The resulting taxonomy was revised by a curator. In contrast to the manual taxonomization, the curator started with a proposed taxonomy, meaning all COVID concepts became leaf nodes and the higher level suggested nodes had unassigned temporary labels, placeholders such as temp ID 1, temp ID 2, and so on. So yeah, input concepts became leaf nodes grouped into the generated 55 higher level nodes with unassigned temporary labels. And curator's approach was to traverse clustered leaf nodes and assign meaningful names to each of these 55 parent concepts, replacing temporary labels. There were 3 usual activities happening during this part of the task. So first was to understand the meaning of concepts within a cluster. Then the curator was identifying what concepts had in common and used that as a label for their parent node. For example, in the upper right cluster, rename temporary ID 25 with cases in the corner. And the third activity was to move concepts that semantically do not fit out of the approved cluster. Now, you probably have this question in mind: what is a good clustering or bad clustering anyway? Even though we did not quantify the semantic soundness of the generated clusters, most of them were pretty accurate. For example, this cluster with temporary ID 69 required no curation at all in the meaning test. Of course, there were grouping errors, likely triggered by corpora used to pre-train fast text embeddings. Like here, interstitial space, which is space between cells, and hospital pharmacy were wrongly clustered together. As for word embeddings, both concepts are spaces appearing in the similar semantic neighborhoods. And of course, some existing concepts became parent concepts as well. For instance, the curator decided to make the existing containment measures concept the parent of civil confinement, disinfection, infection control, and quarantine. This is a part of the backbone of the resulting semi-automatically created taxonomy. When we look at the pure task, namely to name the clusters, clean them semantically, and to finalize the draft taxonomy, the curator benefited from the very systematic approach. And the overall task could be separated into slices of work, and the progress, say 15 out of 55 clusters reviewed, was visible. And as a consequence, the individual motivation was quite high. And what about performance comparison? Well, this table quantifies the effort spent on both manual taxonomization and curation of the automatically created taxonomy. We can see that the collaborative human AI approach is efficient, being 5 times faster than a purely manual taxonomization. It is effective since it doesn't require drastic context switching and semantic jumping, since we systematically name clusters and clean groups semantically. It is scalable, and curation can be parallelized by branch. It is measurable since we can answer how many branches are left to curate, and more systematic than starting with a flat list of concepts. So when we compare 2 approaches from a pure working style, there is a significant advantage to start with a draft taxonomy instead of being faced with this long to-do list. We just go cluster by cluster, section by section. And even when the clustering fails, the main topic someone is working on remains stable. The following figures show the structural differences between the concept maps of the two approaches. So the semi-automatic taxonomization algorithm encourages a strictly hierarchical tree-like concept system. In this study, the proposed taxonomy had only so-called mono-hierarchical relations between concepts. In the manual taxonomization, the curator often hooked concepts under more than one parent, creating a so-called polyhierarchical taxonomy. Some concepts can indeed be hooked underneath more than one general concept, and for instance, the concept Corona response investment initiative can be at the same time a child to emergency assistance instrument, small or medium-sized enterprises, and labor market. Over time, however, this multiple hooking led to quite a multi-linked knowledge net. So if you still wonder about the benefits of taxonomization, here they are. Taxonomization is an effective way to add structure to data and improve its quality. It ensures easier and safer data maintenance. It is generally formalization of knowledge that becomes machine digestible and ready to boost the performance of machine learning algorithms of your choice. Now, let's have a look at a typical industry scenario. So content, topic, and document classification. This is just one of the super typical industry tasks. In case you need a refresher what classification process is about, here it is, schematic. Yeah, the documents that we use for our test were predominantly scientific papers in the medical domain related to the COVID pandemic. In their original form, these documents are unlabeled. So in order to label them for training, we utilized a term extraction tool and got 5 most representative keywords from each document. And for each of those keywords, we check whether there was a similar term in our created gold taxonomy. If it was the case, we would traverse the taxonomy upwards towards the root and find all parent terms of the matching term. Then we would assign the top 2 terms of the parent chain as labels to the document at hand. And after balancing, the final set of distinct document labels had 13 labels. So we were then able to split the data set into standard training, development, and test partitions and proceeded with supervised classification. Before I proceed to performance metrics, I briefly want to share with you an example of our data points and also what true labels and predicted labels look like. And I want to make an emphasis on the granularity of these labels. So we trained 2 convolutional neural nets. One was non-initialized and the second was initialized with the created taxonomy. For both, we used a word2vec model pre-trained on a PubMed's corpus. The non-initialized convolutional neural net had its final dense layer randomly initialized, and the second one had its dense layer initialized with the values that leverage the structure of the created taxonomy. So the idea is to initialize this final hidden layer with rows that map to co-occurrences of labels in the training data. And this can be implicit hypernym relations between the labels or explicit co-occurrence in the annotation. And for each co-occurrence, a special non-zero value is assigned to the associated classes, and a value of 0 is assigned to the rest. The motivation for this initialization is to incline units in the hidden layer to be dedicated to representing co-occurrences of labels by triggering only the corresponding label nodes in the output layer when they are active. It is a form of embedding the structure of the taxonomy into the hidden layer of the neural net. Zero-shot models were made available by the Hugging Face, and it basically means that a classifier can make predictions without prior training examples. It only requires the input text and a set of available labels. Here you see the micro averages expressed as percentages yielded by our tests. Initialized convolutional neural net showed the highest score compared to the rest. And we concluded that the initialization successfully aided the prediction on the unseen data. Still, to increase this performance, several resources can be leveraged. This could further lower the effort needed to taxonomize heaps of concepts using the suggested process. You realize that any project revolves around a specific domain that usually features a specific vocabulary. And well, let's take virology or medical terms in general for our case. So to create more accurate vector representations for these tokens, the specific context in which they apply must be exploited. A corpus of documents directly related to the domain can be used to retrain or tune word embeddings instead of using a more generic model. Moreover, consistent presence of metadata in the terminology can aid the taxonomization process. And if there is metadata about the semantic parent of a term, this valuable information can be leveraged as well. Definitions of terms can be part of such metadata. Well, they can describe the type of a given concept, and often these definitions have a certain structure or follow a pattern. For example, in IATE, there is a term modified live virus vaccine, and it has the definition vaccine made from an isolate of an attenuated virus. So using NLP tools, we could extract the broader concept vaccine and use it as a parent node in the taxonomy. So we believe that the suggested approach can significantly bring down the effort while yielding a taxonomy of a decent quality. And we encourage everyone to try out if you are looking for ways to enhance the performance of your AI solutions. Such taxonomy would let you label your documents automatically, allowing for a finer granularity in results. While our corpus contained only English documents, the labeling process is, of course, not limited to the English language. And say in Cororean, we can support such multilingual concepts. So once the concepts are taxonomized, the knowledge structure is available in all languages. Thank you for your attention. In case you have any questions, feel free to email me or shoot me a message in social networks. And please check out Cororean. We have publicly accessible taxonomies that you can explore. And please enjoy the rest of the talks. Ciao.